Okay, so good afternoon, and thank you to the organizers for this opportunity to present my work. I'm Karen Palacio-Rodríguez, and today I will present you the method that we are proposing with my supervisor, Fabio Pietrucci, to obtain data-driven Langevin equations from transition path sampling trajectories. So first, I want to state the central problem we want to study, that is the dynamics of complex systems. It means that system that has many atoms, different molecules, solvent, and so on, as this fuller in dimer in water. And basically, we can study the dynamics of this system with molecular dynamics, but making long molecular dynamics trajectories is expensive, and taking track of all the many degrees of freedom of the system is also difficult. So to understand dynamics of the system, we project the dynamics on collected variables. So if we follow the evolution in time of these collected variables, we can end up with time series of the CV values or trajectories. So in these trajectories, we have a more simpler description of the what is happening in the process. So here I will make a parenthesis to explain you an important quantity that we are going to talk a lot in this presentation, that is this tau, or the time resolution of the trajectory. That is the time between two consecutive points in the trajectory. So if you have a low resolution trajectory, you will see less detail in your trajectory, and you won't see correlation between one point and the other in the trajectory. So you will have like Markovian behavior. And closing this parenthesis, so what we can do once we have the trajectory is that we can describe the dynamics of the system with the generalized Langevin equation. So in this generalized Langevin equation, we have the collected variable Q, we have its momentum, the free energy, and the memory kernel and the random force. So if we have a very long trajectory, we can compute the free energy as the logarithm of the equilibrium populations. However, computing these long trajectories is expensive, and that's why there are many methods that aim to enhance the sampling and compute faster this free energy. And also the same story happens with the memory kernel, that as we will see today in the following talks, there are many methods to calculate these memory kernels. And what I can tell you now is that we can relate the memory kernel with the random force by means of the fluctuation dissipation theorem. So both free energies and memory kernels are difficult to estimate, but for example, if we want to estimate the memory kernel, we can use this method proposed by Daldrop a couple of years ago, in which we calculate the memory kernel from the correlation functions that involve the velocities, the accelerations, and the average force. And I apply this procedure for two different systems that are interesting to us. That is this fuller in dimer in water, in which I follow the distance between the two fullerins, and I found a memory of the order of picoseconds. And on the other hand, I follow the nucleophilic substitution of the chloromethane. This reaction, so you can see that we find a memory of the orders of tens of femtoseconds. So you see that this memory kernel depends on the system. So it's very important to have into account these memory effects, and that's why we are in this workshop. However, if we want to simplify the Langevin equation, we can assume a fast decay of this memory kernel. And in this case, we end up in the standard Langevin equation. So the fluctuation dissipation theorem simplifies, and we have this small gamma, or the friction, and this eta that will be a Gaussian white noise. So here it's important to remark that when I said fast, it's fast compared with the observation time scale of interest. So for example, fast compared with the transition path time. Then if we go further, we can go to the limit of strong friction when we assume no acceleration. And in this case, we end up with the overdamped Langevin equation. So here we introduce the diffusion coefficient D to avoid dealing explicitly with the mass in the equation 4. So importantly, we consider a case where we can have a generic coupling between the coordinate and the path that lead us to the position-dependent diffusion coefficient. And in this case, this is like more natural to deal with physically motivated collected variables. So a cool feature of this equation is that it has a correspondent Fokker-Planck equation that in this case is the Smoluchowski equation. And what is important here is that if we find the Langevin equation that describes the dynamics of the process, we can recover directly the free energy landscape, the diffusion profile, and also we could recover kinetic rates. So how is this related to our main goal? Well, what we want to do is use these Langevin models to estimate free energy landscapes and kinetic rates or rate events. So basically we want to construct Langevin models, but also to use them to obtain these important properties. And to do so, we need to know to what extent optimizing Langevin models is a way to recover accurate thermodynamics and kinetics. So to answer this question, we have some issues. The first one is what type of input data and what amount of input data do we need to construct the Langevin models. So we need ergodic trajectories or short trajectories will be enough. Also, we need to answer the question if we can predict the accuracy of the Langevin models based on simple diagnostics, because we can always construct a Langevin model, but we need to know if this Langevin model is accurate. Also, we want to know if we are able to propose a methodology that can beat other well-established enhanced sampling methods in terms of computational efficiency and also accuracy. So what we propose is very simple. We propose a conceptually simple and computationally efficient method that allows us to construct data-driven Langevin models of rate events by using likelihood optimization. So there are other methodologies that also allow you to construct data-driven Langevin models as used in the literature, but we want to go a step further and use these Langevin models to obtain thermodynamics and kinetics information. So basically the overall proposal is here in this picture. So I will explain you in detail later, but here I can tell you that we start from molecular dynamics trajectories that are unbiased molecular dynamics trajectories. And from the information in the trajectories, we can optimize a likelihood function using an iterative procedure that I will explain later. And from the optimization of this likelihood function, we obtain directly the optimal Langevin model. It means we obtain the free energy and the friction profiles. And with these two, we can compute new trajectories to obtain the kinetic rates. So going step by step, we start from unbiased molecular dynamics trajectories. So basically, we start by saying that the information we need to optimize the Langevin models is in the trajectory, so in the position in time of the system. So basically, here I have a plot of a typical rate event. So you see that with molecular dynamics, we spend most of the time sampling the minimums of free energy, but the region that is more interesting for us, that is the region of the barrier, is less explored because you have a waiting time that is much larger than the transition path time. So what we propose is that we can use methodologies that are focused on these transition paths, like, for example, transition path sampling. So using these methodologies, we are sure that we obtain good mechanisms, we obtain good transition path trajectories, and we focus the sampling in the region that is more interesting to us, that is the region of the barrier. And this is more computationally efficient because we are not spending a lot of time in the minimum. So once we have these input trajectories, we can go to the likelihood optimization, so we can maximize the likelihood to observe these trajectories given the Langevin models we propose. So we can write the likelihood function as a product of transition probabilities that are also called propagators, and these propagators can be obtained from the formal solution of the Fokker-Planck equation. So basically, you can propose this approximate solution in which you can cut or you can stop our first or second order or so on. So for a small tau, if you stop at first order, you will end up with this easy equation that is in a Gaussian form, where A is the drift term. But if you want to go to a second order to have more accuracy, you will end up also with a Gaussian solution. And if you want to know more about these propagators, you can go to this reference here. But what is important is that now we have the expression for the propagators, and we can write the expression of the likelihood function. So this expression is the one that we want to optimize by maximizing the likelihood, or what is the same, minimizing the log likelihood. So to recap, we have the input trajectories, and we can maximize the likelihood function that we now know how is the mathematical expression. So we can use this algorithm to maximize the likelihood function, in which iteratively we propose changes to free energy and diffusion profiles, and we accept these changes according or reject them according to a metropolis criteria. So from this optimization, we will end up with the optimal free energy and diffusion coefficient profiles. And from these profiles, we can launch new trajectories to obtain the kinetics. So the advantage of this methodology is that we are not using equilibrium MD data. So we are not using long trajectories. So this is computationally efficient. And this can be applied almost irrespective of the height of the barrier. So it can be applied to rate events. And also, we can use these Langevin models to generate new data at a cheap cost, which is very nice, because this is like the key point that can be difficult to achieve with molecular dynamics. So we are aware, however, that we have a problem, and this problem is that many activated processes of interest are not Markovian. And as we are here in this workshop of memory effects in dynamical processes, we know that memory is very, very important. And that's why we are carefully studying when we can describe a system with a Markovian model. So we care about memory, and we carefully choose when our system can be described with a Markovian model. So fortunately, we demonstrate that the key to obtain accurate Langevin models is to find this appropriate time resolution to take into account the Markovian behavior. So I will show you some results, first in a benchmark system and then in an application. So this benchmark system is a Doublewell potential. So here, basically, first we did a obvious check, in which we only want to know if we are able to obtain consistent Langevin models. It means if we start from overdamped synthetic data that we know that we generate with the same equations, are we able to reconstruct consistently Langevin models? So for this system, we have a taken BT barrier, and we start with 100 shootings from the barrier top. So basically, in the bottom, you have the reference free energy profile, so the exact results, and also the reference diffusion profiles in black. And you see that regardless of tau, regardless of the time resolution, that is the color lines. So we have the optimized models for different time resolutions. And regardless of tau, we obtain a almost perfect free energy profile. However, with D, we see that if we increase tau, the accuracy of D will decrease. And this is because when you increase tau, you will have less data to construct the Langevin model, and also the propagator, the approximate propagator you have is supposed to work only for a small tau. So if you go to big tau, you have to be careful with the accuracy of the propagator. Then that we know that we are able to construct consistent Langevin models, we can go further and we can study a system with memory. So now we have synthetic data that has memory, and here is more interesting the question, because here we are saying, are we able to describe the dynamics of this system with an overdamped Langevin equation, even if it has memory? So here we study the same for several tau resolutions, and we have that the answer is yes, we are able to reconstruct accurate Langevin models, but depending on tau. So here I can say that the more accurate model is the one in the orange line, but this is because I have the reference. So in the case where I don't have the reference, so in a real case, how can I tell where the model is accurate? So we propose two different tests to make a diagnostics for the choice of tau, in which you can do the test as a post-analysis procedure, and we care about the memory and we care about the accuracy of the propagator. So first we care about the memory, and to do so, we calculate the autocorrelation time of the effective noise. So from the Euler-Maruyama integrator, we can obtain an expression for the noise, and we have the following hypothesis. If the noise will have been generated by the model, it will be random with zero mean, unit variance, and no time correlation. So we compute the distribution of the noise, and as you see, the overall shape is as expected, a Gaussian function, zero mean, unit variance, and so on. But for big tau, we see deviations for the ideal behavior. And from the correlation function of the noise, we see that for a big tau, you decorrelate in the first step, but for a small tau, you need several steps to decorrelate the noise. Then the second test is related to the propagator accuracy. So basically here we are saying for a fixed Langevin model, we know that our approximate expression of the propagator introduces an error that grows with tau. So to estimate this error, we compare multiple very accurate Langevin trajectories with the second order propagator. And this gives us our second quantity to test the quality of the model. So we have in one side the tests that allow us to care for the memory effects, and in the other side, the tests that allow us to care for the quality of the model. So the orange line tells you that if you go to the right, you will have more Markovian behavior because you correlate faster. But at the same time, the blue line tells you that if you go to the right, you will also lose accuracy in your propagator. So you need a compromise between the Markovian behavior and the accuracy of the propagator. And this compromise is found where the two lines overlap. So in this case, if this is true, we have a diagnostic that allows to say where we can trust the model that we are generating. And in this case, we found that for the from the diagnostics, the optimal tau is around 0.5 picoseconds, which correspond to the orange line that has more accuracy in the free energy. So we are able to identify the time resolution where the model gives more accurate results, which is very nice. And now that we have these Langevin models, we can ask ourselves if we can predict the kinetics from these Langevin models. To do so, we generate trajectories with these Langevin models that are cheaper than the MD ones. And we apply the reactive flux formalism. This reactive flux formalism is a robust method that is free from the approximations of transition state theory. And that basically the only limitation that it has is that it needs a lot of data to converge. But now we don't have the problem of the sampling because with the Langevin models, we can generate many trajectories at a cheap cost. So we apply this formula that is based on the correlation functions. And we have here the HA and HB are the characteristic functions of the metastable states. And in practice, we compute the rate numerically. So we only need the number of shootings, the location of the transition state, and the free energy that we already have it for the models. So here we end up with one of the central results of our work, and is that we are able to compute the kinetics from the Langevin models. So we estimate the mean first passage time, and here we have two important results. The first one is that you see that for a small tau, where we said that the model is not accurate, this is an optimal model. So we are able to optimize a model, but if you see the rate that you obtain from that model that is not accurate is orders of magnitude, like 4 orders of magnitude greater than the reference one. But if you go to the optimal values of tau that we show through these diagnostics, you see that you find mean first passage time that are of the order of magnitude of the reference. So you find accurate mean first passage time for the accurate Langevin models. And having this important result, we can go to an application, a real application that in this case is the fluorine dimers. And in this case, we tested two fullerene sizes, the C60 and the C240, because by increasing the size of the fullerene, we increase the size of the height of the barrier. So we have as input data 100 trajectories from transition path sampling, and we have as collected variable the distance between the center of mass of the two fullerenes. And this is the trajectories that we end up having for the input. So we did the same. We optimized Langevin models for different time resolutions, and this is the free energy profile that we obtain. So from the diagnostics, we have that for C60, the optimal tau will be around 0.6, and for C240, the optimal tau will be around 1. So if we go to the left, we see that around 0.6 and 1 for the C240 is where we have the more accurate free energy profiles. So this test of these diagnostics works. And now we go to the kinetics. In the mass first passage time, we can also make similar conclusions to the one that we have for the Doublewell potential. So basically here, for the optimal Langevin models, you see for the optimal tau, you see that you end up with, for the two cases, with mean first passage time of the same order of magnitude as the reference. And even if you go further, you still have the mean first passage time of the same order of magnitude of the reference. And this is very important because, for example, for the case of the C240, you have that you are reconstructing, you are recovering mean first passage time of the order of microseconds for initial trajectories that are in the order of picoseconds. So basically, you have a total simulation time that is about 10 nanoseconds if you consider all the trajectories, and you are recovering mean first passage time of the order of microseconds. And also we have the same thing that here for the Langevin models that are optimal but not accurate, you have a bad reconstruction of the mean first passage time. So as conclusions, I show you that we are able to obtain Langevin models that can predict accurately free energy diffusion profiles and kinetic rates, and all of this from transition paths. So the advantage of this method is that the only input you need is short empty trajectories. So the sampling could be fast, and also you can choose the collected variable a posteriori, because for the MD, you don't need to choose in advance the collected variable, you can choose it once you are optimizing the models. Also, we propose this optimization with a very simple likelihood formulation, and with this formulation, we can obtain Langevin models that allow us to retrieve mean first passage time order of magnitude greater than the length of the input trajectories. So we know that the main limitation is the use of these memory-less Langevin equations. However, we provide you with some recipes so you know how to assess the quality of your model in post-analysis. So you can say when your model is accurate. So at work in progress, we are now applying this formulation to biomolecular interactions. So we start for this deckbox protein that has this like PACMA behavior. So we want to study the conformational change of this protein, and we are working in collaboration with Alessandro Barducci. Also, we are working with Peter Bolthaus in the study of the beta-lactoglobulin dimer mechanism, because they have a lot of data in the mechanism that you see here is a complicated mechanism. So we want to see if without methodology, we can recover free energy landscapes and transition rates for this mechanism. And also we want to study different protein complexes in biomolecular condensates. We want also we are now working on the implementation of the standard Langevin equation that is work in progress. And as we only need the transition path sampling trajectories, we could think on applying this methodology to the same applications that people use for transition path sampling, like chemical reaction in solution, nucleation of inorganic materials, and so on. And an interesting perspective or idea that we have is to use this methodology on the optimization of reaction coordinates, that if you are interested, you can ask me and I will be happy to explain you. So if you want to know more about it, you can go to this archive that we recently published, or you can write me and I will be happy to answer. And now, because this is a research line that is very interesting for us in our research group, you will see that later today, a talk by one of the postdocs of the group, Adrien Roland, he will talk about an approach in which he used, again, livelihood optimization, but now he used it in a generalized Langevin equation to compute memory kernels. So it's very interesting. Stay tuned, and thank you for listening to me today, and questions are welcome.